Hello everyone, Major Oser here today. Today we're going to look at what we carry in our meter kit on all of our companies. So to give you a better understanding, we've laid everything out of the kit here, and we're going to go through one by one and talk about what they are and what they're used for. The first item we have over here is not actually part of the rae meter system that we use, but it's something we've added into the kit for your use, and that is a combustible leak detector. The combustible leak detector we'll go into a little later on exactly how to use it, but the important thing to remember with it is if you're using this combustible leak detector, the rae meter needs to be in operation in the same space as it, because this only detects combustible gases. It does not tell you the amount of combustible gas present. Next thing we have is confined space tubing. The confined space tubing is exactly that. It's for use when you use the rae meter with confined spaces. It's 20 feet long, and it allows you the ability to stretch the hose out straight and to be able to get away from the confined space opening. The next item is the chemical resistant hose for use during hazmats. You'll notice it's curled up and it's not designed to be stretched out straight, so it would not work well in a confined space. But it does have a chemical resistant coating that keeps it from being contaminated. Last item in this segment over here is the hand wand. That's for use with either hose, and it just gives you something to hold on to. Up here we have a spare battery pack. It's for use with 4 AA batteries, just in case the NiCad battery on your meter is dead. Here we have laminated sheets that include the instructions. They also include the conversion charts that we use, so it's important that those are always in the kit and available. Here we have the charging. Everyone, I think, probably knows how to use this. You just hook it to the end of the meter, and we charge the meters once a week. We have 2 different types of demand flow regulators for use with our 3 calibration gases. We use 3 separate calibration gases that we'll go into in detail when we do the actual calibration of the meter. And finally, the rae system's multi-rae light meter. This is what's carried on all of our companies, so we'll go into how to calibrate it and proper usage here in just a moment. What we're going to go over now is the combustible leak gas detector. Like I talked about earlier, you never want to use this meter without the multi-rae light running in the same space. And the reason for that is because this meter only detects combustible gases. It does not tell you the amount, so it will not alert you to if you're in an explosive environment or not. But what this meter is excellent at is locating a small leak in a combustible line, like a gas line to a furnace or a water heater, allowing you as the firefighter to actually isolate the appliance that's leaking, that has the leak, and turning it off, thereby being able to leave the rest of the gas service to the house on. It's very easy to use. All you do is turn it on. It's going to come up with a loud whine. You gently and slowly want to turn the sensitivity handle down. And you want to bring it down to where you're getting a click every 3 or 4 seconds. Sometimes you have to bring it back up just a little bit. And you get it right into this area where it's clicking just a little bit. And then you can take this instrument down a gas line or to an appliance and see if that appliance is actually leaking. When you get in the area of the leak, and it's kind of like using the hot-cold system, as you get closer to the leak, it's going to start clicking faster. And you can actually trace it right down to where the leak's at, usually in a coupling or something like that, allowing you to turn that appliance off, not turning off the gas to the entire structure. It's powered by a 9-volt battery. It just needs to be changed if it's dead. Besides that, there's no calibration or maintenance with this piece of equipment. Okay, we're going to talk about the rae system's multi-rae light meter now. And the very first thing we're going to go over is how to calibrate and bump test it. To start with, we want to turn the meter on. When we turn the meter on, it's just the center button pressing, holding for a couple seconds and letting go. Now, some folks like to ask a lot of questions about why this meter takes so long to boot up. Well, we have to remember there's two things taking place here. One, the computer is warming up. This is actually just a mini computer. The other is the sensors take time to actually heat up to a temperature where they can actually operate and detect what they're supposed to. So this warm-up process is both of those occurring. What we're going to do today, we're going to talk about calibration and bump testing, but we're actually going to do a calibration. The bump test is conducted exactly the same, except it's a shorter thing. And we'll talk about the difference of calibration and bump testing while we're doing some of this and we have some time to get through. This warm-up process, as it's taking place now, you'll see it's warming up and it goes through all the sensors that are in it. The meter has finished its warm-up phase now, and the first thing that actually requires some interaction from you is the fresh air setup. Now, the fresh air setup, I'll go ahead and hit start because we're in a spot where we know we've got fresh air. That takes 60 seconds for us to do its fresh air setup. It's important to remember when you're doing a fresh air setup, we don't want to do this in a contaminated environment like an apparatus bay or on scene, possibly in the gas leak, or even worse, standing next to the exhaust of the apparatus. We've had good success doing fresh air setups on the way to runs in the back of the apparatus because there's enough air movement for that to allow a good clean setup. If you start a fresh air setup, you can always quit and come back and do it again if you started it in a contaminated environment and you realize it. However, if you go all the way through the fresh air setup in a contaminated environment, what ends up happening is you've told your sensors that the air was clean and that everything, once this is finished, it's supposed to start metering, and you've given them a false start point. So it actually throws all your readings off from there. During the calibration phase, when we're calibrating, if you've done your fresh air setup like in an apparatus bay where trucks have been running or equipment's been running, it's going to mess up the calibration. The most likely fail that you will get will be on the VOC, which is volatile organic compounds, which is from the reading on the PID, the photoionization detector. That's the most sensitive piece of equipment inside this meter, and it's very susceptible to having a bad fresh air setup, and you'll find your calibration will fail. If your calibration fails on the VOC, that is most likely the cause is that you've done a fresh air setup in a dirty environment. All right, we've finished with that. It's done its fresh air setup and it's ready to go. What we've done with these meters is we've programmed them to require a bump test every 8 days and a calibration every 40 days. We generally would like to have all the meters checked every week. On the first weekly check of the month, we want to do a calibration. On all the rest of the weekly checks per month, we want to do a bump. This meter is calling for a bump check right now, but since I want to show you a calibration, I am going to go ahead and skip through it. If this shows up on scene, you don't have to stop and do it. You can actually go ahead and go through it. You just understand that the instrument, the bump check, is trying to figure out if the sensors are all working properly. And I'll talk more about the difference between a calibration and a bump as we're waiting for some of this calibration to take place. All right, I'm going to skip it so we can move on. All right, the meter goes into its normal mode now. So this is, if everyone has done all of their checks appropriately, this is where you will find the meter after the fresh air setup. To get into the menu and actually do a calibration, all you do is press the center button and the right button at the same time, hold them, until the password screen comes up. Now we have the meters locked out now, so you can't go back and mess with any of the programming. However, all you need to do at this point is just hit done, and it will go on through and let you do the things that you're allowed to do, one of those being calibration and bump testing. The little cylinder here is the calibration and bump screen. It's already highlighted. Just hit select, and then comes up a menu. Now, you notice I've talked about calibration and bump testing, and as we come down the menu, you could redo a fresh air setup, so that allows you to redo it if you started it in a dirty environment. Then it talks about a multi-sensor span, and you're like, okay, we haven't talked about span at all. What's a span? Well, in the meter world, span and calibration are exactly the same thing. Everywhere else in this meter, it's going to talk about calibration, except right here, it's going to call it a span. The other thing, you can do a single sensor 0, single sensor span, multi-sensor bump, or single sensor bump. Why would you choose the different items? Well, if we've already, say you had a dirty setup and you wanted to start all over, you could choose one of the single sensors, or if you think you have a bad sensor and it's already failed an initial test, you can just do the single sensor check to see if that's working properly. But normally what we're going to use is either the multi-sensor span or the multi-sensor bump. Today, since we're doing a calibration, we're going to use the multi-sensor span. And all you do is come down, use the arrow to come down until that's highlighted, and hit select. And then it's ready to go. Set the meter down, and we'll grab our calibration gas. Our first calibration gas is multi-gas, and it always starts in this order. You'll notice 4 sensors are ready to go, and they correspond to the 4 sensors on here: carbon monoxide, hydrogen cyanide, methane, and oxygen. The methane sensor is our LEL calibration gas. When you go to hook this up, well, first of all, before you get started, make sure you have calibration gas in your cylinder. If you don't have calibration gas, it will fail the test. Now we want to use these cylinders down to empty. They're very expensive, so even if the cylinder's showing almost empty, go ahead and try to do a calibration. If it fails during the middle of it, that's okay. We can get you more calibration gas. But they actually go pretty far where they actually look like they're empty. So the easiest way to do this is turn the meter upside down, connect, and rotate. That way you can see the meter during the test. Then hit start. This first calibration lasts 240 seconds. The reason for this is one of the sensors involved is the hydrogen cyanide sensor. Hydrogen cyanide sensor is what's known as a long soak sensor. It takes an extremely long time for this sensor to respond to the hydrogen cyanide gas. Now, this is important because when you're using this meter at like a fire scene to measure for hydrogen cyanide to make sure we can come out of our air packs, you have to slow down. Remember this 240 seconds. When you walk through a building, you need to spend 3 or 4 minutes in each area of the building where you're taking readings to give this hydrogen cyanide sensor time to adjust. And if you watch the sensor as it's adjusting, as you're going around taking readings, you can see when it finally stops fluctuating a little bit. That kind of lets you know that you've reached where it's going to level out at. But if you just walk through a building as quick as you can, you'll be taking readings 2 or 3 minutes behind where you're actually standing. So that's an important thing to remember as we're using this meter on a scene. Okay, we got just a couple minutes here. Let's talk about calibration and bump testing. Calibration is actually adjusting the sensors to the known calibration gas. You can think of this very similar to putting a known weight on a scale and adjusting the scale to that known weight. We're actually telling the meter to move the sensor to that known amount of gas. That's one reason that this takes so long. It takes time for the sensor to get to where it's going to level out and then make the adjustments. A bump testing is not the same thing. A bump testing, all it does is it puts the gas onto the meter, and then once the meter is within 10% of the calibration gas, it says the sensors are working fine and I'm done, and it passes the sensor. If for some reason the sensor has drifted farther than 10% away from the calibration gas, it will fail the sensor. If you fail a sensor during a bump test, you should go back and try to do a calibration. These sensors drift over time. As they get older, they start to drift a little farther, a little faster. So some of our sensors, we don't replace them until they actually go bad. So some of them are 3 or 4 years old, and as they get farther away from that being that new manufacturer date, they drift farther and they drift quicker than the month. Looking down, we still have 30 seconds to go. So the big thing to remember is the bump test is not a calibration. It does not adjust the meter, and if that gas does not come within 10% on the meter, it's going to fail that bump, and you'll have to go back and recalibrate the meter. No big deal, it happens sometimes. As far as the bump process, it's exactly the same though. It just doesn't last as long. Okay, we're winding down to the end here, and we'll see if the meter has adjusted all of the sensors to this known calibration gas. It will come up with 4 passes. If something is wrong, it will fail it. All right, we have 4 passes, so we can move on. All we do is remove the gas, and we'll get another calibration gas. One of the things we want to do during this time is give the meter a few moments to run on this fresh air and just kind of get itself balanced back out. We just flooded the meter with a bunch of different gases, and if we do this calibration or bump test, either one, as fast as you can do it, what's liable to happen is you got some cross sensitivities on these sensors and you'll fail one of them. It's no harm to let it sit here and run for just a minute before we move on to the next product. The next thing the meter has been programmed to ask for is H2S, which is hydrogen sulfide. So we hook this up in exactly the same way. We'll turn the meter over, bring it up to the port, and twist on till it's like that. And then we'll want to hit calibrate yes, start. You'll see this one only lasts 60 seconds. That's because we don't have that long soak time that's required for the hydrogen cyanide sensor. Less than 30 seconds to go. We'll be done with this one. The next step, we'll move on to isobutylene here in just a second. When we get to the isobutylene, you'll notice it's in a different color cylinder. Sometimes they're blue and sometimes they're yellow. They're actual steel cylinders instead of the aluminum cylinders because the nature of the gas, it has to be in a different cylinder. All right, we'll see if this one passes. It passed. Okay, we'll give it just a moment to clear out while we get this cylinder ready. The cylinder of isobutylene uses the other gauge because it's a steel cylinder, and then you'll see it's labeled isobutylene. We use this to calibrate the PID, the photoionization detector. And it gets a little confusing because the PID actually shows up on your screen as VOC, volatile organic compounds. We'll very quickly talk about the operation of the meter here in just a moment. This is not an entire meter class, but we'll talk about individually the sensors and what your reaction should be here in just a moment. All right, we've probably given it long enough to breathe. Let's go ahead and get ready and do this last calibration. Put the meter on, tell it you want to calibrate it, and to start. Once again, this is only a 60-second calibration, so it doesn't take too long. When we finish calibrating the meter, we want to let it set and run for about 10 minutes in some fresh air to let it clean out all those sensors that we've just flooded with gas. We really don't want to just turn it off as soon as we're finished and stuff it back in the case. So today, as we're doing that, we're going to talk about some of the operations just to get through and give you a brief overview of the different sensors and what your reaction should be with these sensors. All right, it passed. So we finished the calibration. Now we're going to hit back. And we'll have to hit back once more. It's going to apply everything. And you're going to see we're still reading some high readings. The HCN is still high now, and that we did that that was one of our first gases. So we're going to sit here and let this clear out and come down and talk about the sensors. Our first sensor we'll talk about is oxygen. I think everyone understands oxygen is very important. It's what allows human life to exist on the planet. So our meter is set to alarm in high oxygen and low oxygen both. So if you get an alarm on the oxygen sensor, the whole meter will flash red around the lights, and then that sensor will alarm, telling you either got low oxygen or high oxygen. And obviously at that point, that's when you need to consider what's causing that situation. If it's low oxygen, you need to go ahead and use your SCBA and figure out what's displacing it. And then if it's high oxygen, you probably have an oxidizer in the environment and a higher risk of fire. So you want to figure out what's causing that oxidizing to occur. So the next sensor we have, I'll turn the light back on, is LEL, lower explosive limit sensor. This is a scale of 100. So it measures, it's calibrated to methane, which methane is basically natural gas. So the idea behind it is that's the most likely thing that you're going to come in contact with is natural gas. So it is designed to go into alarm at 10% of the lower explosive limit. 100% being the actual spot that becomes explosive. That has a 90% safety factor built into the meter because a lot of combustible gases are a lot more volatile than natural gas. So that safety factor, if you're going up against propane or butadiene or something that has a much higher volatility, it gives you that safety margin to be able to exit the building. Obviously, this is a sensor where we're not going to put on an air pack necessarily, but we're going to get out of the structure, ventilate, and figure out what's causing the leak. All right. Next one down here is CO. That's carbon monoxide, byproduct of combustion. Our sensor's set to go off at 35 parts per million. Well, that's a relatively low number in comparison to something that's in an environment where there's a big CO leak. The reason we've set it so low is because, one, that's the NIOSH standard. And then also it allows you time to put an air pack on. Usually if there's a CO problem inside of a house or a building, usually a few steps into the front door, this meter will go into alarm and the CO sensor will be flashing and you'll be getting high readings. That way you know to go ahead and back out, put an SCBA on, and go find out what's causing the CO problem. Next is hydrogen sulfide, H2S. We have that sensor in because of its ability to hang below air. It likes confined spaces. It likes anything below grade. It's heavier than air, and it's a very deadly gas. So this meter is set to go off at 10 parts per million. It's important to remember the ideal H for hydrogen sulfide is only 100 parts per million. If you look around the country every year, we kill 2 or 3 firefighters from hydrogen sulfide exposure where they didn't have this meter out and they went into a confined space and they were overcome by hydrogen sulfide. So we always want to have this meter out and running anytime we go below grade. All right, next thing down here we'll talk about is hydrogen cyanide, HCN. This is the one that came into the fire service a decade ago. And the reason they're tracking it is because it's pretty much present at all fires now. And it allows us to know the amount of hydrogen cyanide in the air, usually after a fire, in a structure. We can go in, we'll meter for it. Our requirement on this is 5 parts per million. This is a cumulative gas, so it builds up in your body over time. And this is one of the ones that leads to cancer and while we're trying to eliminate it. So, and remember, this is the slow soak sensor. It takes about 2 to 3 minutes for it to get where it's going to go and level off. So when you use this at a structure fire, make sure you slow down and give that sensor time to adjust. The last thing down here says VOC. VOC is the reading in parts per million from the PID, the photoionization detector. There is a product, there is a list of products that this measures up for. It measures any volatile organic compound. There's a list of about 8,000 different things it measures. It's measuring them, though, in relation to isobutylene. It thinks that isobutylene is what it's looking for. We use our conversion charts to figure out the exact exposure limits. But the important thing to remember with this sensor is this is your respiratory protection sensor. A lot of fire departments do not carry this sensor because it literally makes the meter triple the price. We carry it because it's so important in protecting your respiratory health. This alarm is set at 50 parts per million. It's going to go into alarm. It's not going to tell you which of the 8,000 different products that it's looking to see is actually out there. It is going to tell you something is there and you need to put on your SCBA. So with that, the important thing to remember with these different sensors, what are your actions? Well, 5 of them are pretty simple. If it's oxygen, CO, H2S, VOC, or HCN, the answer for a firefighter is put on your SCBA. If it's the LEL sensor, the answer is evacuate and ventilate. All right, that concludes our presentation for today. To turn the meter off, we've pretty much zeroed everything out here. So we will press the button, hold for 5 seconds, and you're finished.